This is example 16.1 from Discovering Design with Chemistry, and yay, you have made it to the last chapter. Alright, so chemist performs the following reactions, starting with NO and H2, each at a concentration of 0.100 m, and both products at a concentration of 0 m. And then they give you the reaction with the little double arrows, because now we're talking about equilibrium. At equilibrium, the concentrations of NO and H2 are 0.024 molarity. The concentration of N2 is 0.38 molarity, and the concentration of H2O is 0.076 molarity. What is the equilibrium constant for the reaction? So we have an equation to work with that, so we're just going to start plugging things in. So we want the equilibrium constant, that is K, and we're going to plug in. Notice again, just like a lot of the other ones where we're starting with products and subtracting reactants, like in chapter 14, I think it was. Now we're starting with products and dividing by reactants in this chapter. So, and the little exponents this time in this chapter are indeed the coefficients that are in the reaction equation. So we're starting with nitrous, and for this part we want the concentrations. I couldn't fit in the little EQs here on the equation like the book has. That's what this part means, because I couldn't make a subscript and a superscript at the same time. It was just unhappy about that. So this is N2, and this is the concentration at equilibrium. So we want to have N2, there's our concentration at equilibrium, so 0.038 m, and that's at equilibrium. And then that has just, there's an imaginary 1 in front of it, so this would be raised to the 1, but I'm not going to write that. The next one is H2O, and again we care about the thing at equilibrium, so we're going to use that number, 0.076 m. This one does need an exponent because it has a 2 here at the beginning of the equation. I mean at the beginning of that particular molecule. Alright, now we're doing the reactants. So NO, gas, the concentration of this one and the other one, so both numbers on the bottom are going to be the same thing. 2,4 m. This is at equilibrium, and this one has a 2 in front of it. The H2 is the same number, and it also has a 2 for its coefficient, so that's going to go in front of it. I could actually combine these two and just raise it to the 4th power, because 2 plus 2 is 4. But if you're like, what? I don't remember that part of algebra, don't worry about it. Just type it all into the calculator. So I'll show you how to type it in without making any changes to the thing. Put my pen down. Okay. So the top is 0.038 times, I'm going to put this one in parentheses because I want to let it get squared first, to the 2. Alright. That finishes the top, and I'm dividing by everything on the bottom will go in parentheses. Another parentheses for my 0.024 to the 2 times a second 0.024 to the 2. Close that parentheses, close the bottom parentheses, and then hit equal. Okay, I have on all those numbers 2 significant digits, so that's all I get in my answer. So the 6 and the 6 are the only digits that can be significant, so I'm going to round to the tens place, so 660. So K equals 660. Let's look at our M's. I'm just going to kind of put this over to the side. I have an M and then an M squared on top, and on the bottom I have an M squared and another M squared. So if you look at those, this would cancel with this would cancel with one of these M's, so I'll just mark out the 2. So my units for this reaction are 1 over M. If I had different not concentrations, if I had different coefficients in the equation, my units would be different. So the value for the equilibrium constant has its units changed based on the coefficients there. Was there anything else in this thing I needed to point out? Nope, I think that's it. Okay, easy peasy. Just plug everything into the thing and watch your units.